Welcome to my video report for Lab 3 Black Hole. For this experiment, we were analyzing the motion of the star orbiting a black hole of an unknown mass located at the origin. The star mass was 2.0 times 10 to the power of 30. The position data were generated in the code. We assume that the net force on the star is due solely to a black hole located at the origin, and that the time between the points in our trajectory is 1 day. So the final goal of the experiment was to estimate the mass of the black hole. On this slide, I have summarized the most important concepts used throughout the experiment, such as Newton's second law and the gravitational force, the relationship between the change in the momentum and the net force, the derivative form of the momentum principle, and therefore the fact that the momentum can be divided into two components. Now we calculate the net force using the derivative form of the momentum principle. Delta P equals F net times delta T, and so we obtain that F net equals delta P over delta T, and as delta T goes to 0, we say that net force equals dP over dt. On this slide, I have a detailed description of how to obtain the perpendicular and parallel components of the net force from the rate of change of the momentum. You may pause the video to read it in more details. Most importantly is that in the GlowScript code, we first calculated net force and its parallel component using the rate of change in momentum formula, and then obtained perpendicular component by subtracting F net parallel from net force. And finally, we calculate the mass of the black hole itself. The general formula that I used is 1 of the magnitude of the gravitational force. And from this formula, we obtain the expression for the mass of the black hole. Now in the code, we plug in the corresponding numerical values and obtain the final expression. MBH equals magnitude of force times start position minus black hole position squared divided by the mass of the star times gravitational constant. Then the code uses this expression to generate different mass values. So I have copy-pasted them all to the Excel worksheet to obtain the average mass of 1.4692 times 10 to the power of 34 kilograms. Here you can see a few screenshots from my GlowScript code that are related to the previous discussion. On the lines 164 through 172, I have calculated the change in momentum. Lines 175 to 189 are all about setting up the net force and its components using the change in the momentum principle. On the line 193, you can see the mass equation discussed on the previous slide. On this slide, I have included the portion of the code related to errors drawing for the net force and its components. Net force is an orange error, perpendicular component is the pink error, and the parallel component is a blue error. On the screenshots, we can also see that Fnet and Fnet perp do not change their direction, when Fnet par of the second picture points in the opposite direction. Now let's discuss how the net force and its parallel and perpendicular components are different from the rate of change of momentum and its parallel and perpendicular components. Fnet and change in momentum dp/dt are two different things that are connected by the momentum principle. Net force is obtained by adding up all forces of the system together. dp/dt is related to the system's motion. Knowing that the net force, you can use the momentum update equation to calculate the change in the momentum using the following formula: delta p equals Fnet times delta t. Answering the what if question, I think it is impossible to calculate the mass of the black hole different from the original one, because if the mass is different, then the net force will be different, and therefore it won't follow the exact same trajectory and patterns in general. And lastly, how the experiment could be improved. First of all, please notice that the dataset we are using for generating the average mass value is not continuous. And in addition, we know that if the time step is too small, because of the computational resources, we'll see a round of error, since we would be calculating the same thing over and over again. And at this point, we cannot determine whether the time slot of 24 hours is too small or too big for the experiment, which might also be the source of error.